One of the key tools that statisticians have at their disposal in the world of inferential statistics is the concept of estimation. The next couple of videos are going to detail how statisticians use estimation for population proportions and population means, but we're going to start in terms of proportions. Let's return to an example you've seen before in a previous video where there's the population of US adults, which is represented by this picture here. And our variable of interest is political party preference. So that could be, whether they're Republican, Democrat, other, independent, whatever it is. We're specifically just going to concentrate on the proportion of people that are Republican for argument's sake. Okay. So remember the variable P right here represents the true proportion of US adults that are Republican. This quantity is unknown. We don't know this. We didn't ask every single US adult what their political party preference is, and that has never happened. Even in the census, they're not going to reach everybody. So that is a truly unknown quantity, the variable P in this scenario. So what do statisticians do in order to possibly figure out what the quantity of P is? Well, they take a sample. Let's not really worry too much about how many are in the sample. Let's just say it's a big sample, right? They take a sample, and what do? They compute the true sample proportion of US adults that are Republicans. Then they take another sample. Let's just say large sample, okay? And then they compute another sample proportion of US adults that are Republicans. And they obviously just keep on doing the same thing, right? P hat 3 and so forth, people. You just keep on doing that. So we have a bunch of samples that we could take in order to estimate what P is. Okay, let's get a little bit more formal now. We say that the sample proportion P hat is considered a point estimate of the population proportion P. We use the term point estimate when we have an unknown parameter, such as the population proportion P, and we need some statistic to estimate it. The best possible one that we have is P hat. So we say that P hat is a point estimate of P. So a popular question a student might have would be, does that mean we can just use one random P hat, such as this one, as a direct replacement for the population proportion P? The answer is no, we can't. Why? Because as you know, as we take all of these different P hats, they're likely to be different. They could be the same, but they're likely to be different. In other words, there's a lot of variability among all of those sample proportions that we take. So therefore, using it as a direct replacement for the population proportion P would not be a good idea. But if we could somehow come up with a measure of uncertainty in using this sample to estimate this population, then we would be in business here. And that's exactly what statisticians did. Whenever they have a point estimate, such as P hat, what they do is they always accompany that point estimate with something called a margin of error. Most students have heard of the term margin of error before, but let's talk about what that means in this direct scenario. So again, if we took the sample right here and we end up with the proportion of, let's say, 35% are Republican, we cannot just directly say that the population is 35% Republican. We can't do that. So what a margin of error helps us with in every single sample that we take is it gives us a plus or minus some value where we can go a little bit below the sample proportion of 35%, maybe 2% below, and then 2% above, let's say. And that'll give us a span of values that we can use to estimate the population proportion instead of using it as a direct replacement of it. Note that this span of values that I referred to is actually formally called a confidence interval, which is one of the big topics in inferential statistics and basically all of this chapter. A confidence interval is defined as a point estimate, such as our value p hat, plus or minus the margin of error. While there are many different confidence intervals in the world of statistics, two of which that you will learn in this course, specifically for estimating population proportions, we would say that the point estimate is going to be p hat, as discussed over here, plus or minus the margin of error. We use the variable capital E to represent the margin of error. We'll have a more in-depth formula for that a little bit later. Okay, so before we move on, let's just give you a scenario of this example. So remember, we're doing political party preference, specifically the proportion that are Republican. We're trying to estimate the proportion that are Republican in the US population. And we currently have, let's say, one sample that we're dealing with. So let's say that we did that sample and we got a sample proportion of 0.35. And the margin of error in calculating this ended up being 0.03 or 3%. So we have 35% of the sample are Republicans, and the margin of error accompanying the calculation is 3%. Then what would that do? Well, that would give us 0.35 minus 0.03 on one end, and 0.35 plus 0.03 on the other, which would give us on the low end 0.32 as our proportion, and on the high end 0.38. So we normally, by the way, use interval notation to represent confidence intervals, just something like that. So what does that mean for us? And in this example, well, we couldn't use 0.35 as a direct replacement for the true population proportion, but we, along with the margin of error, can estimate the true population proportion as somewhere in this span. Now, there's more to it than that, because there's going to be something called confidence, specifically a confidence level, that's going to add to this sort of situation or this concept, but just informally, that is what we're trying to do. We're trying to use a span of values to estimate the true population proportion, because we can't just use p hat as a direct replacement without some measure of uncertainty to accompany it. The next step is to talk about the actual formulas for this process. So specifically, we refer to something called a 1 minus alpha times 100% confidence interval for a population proportion as p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. Okay, so we have our point estimate right here. Point estimate, which is our sample proportion, p hat. And then on this side, as stated up here, we have our margin of error. Now take note that a lot of the variables and formulas involved with this should be very familiar to you, but there's also going to be a lot of unpacking before we can get to any type of computations here. Okay, so let's start with the margin of error portion of this formula, since p hat is pretty self-explanatory in the point estimate. So what you'll see basically is there are two parts to the margin of error. The rightmost part should be somewhat familiar to you. If we go back to the previous lesson on sampling distribution of sample proportions, if you recall, the sample proportion had a standard deviation of this, square root of p times 1 minus p over n. So that is almost exactly the same as what we have here. The only difference is that we're using p hat instead of p. Well, why are we doing that? Well, aren't we trying to use this interval to estimate p? We note that p is unknown, which means how can we use it in the formula like this one? We can't. So what's the next best substitute for p? It's p hat. So generally, this is the standard deviation for the distribution of p hat, but with p hat replacing p. This part of the formula is routine. Why? Because every problem that you're going to get, you're going to be given n and p hat, which means all you're doing is just plugging in the numbers into that part of the formula, and it will be very simple to compute. The other part of the formula, on the left side over here, is not as straightforward yet. So remember, this is called z sub alpha terminology. So we're going to call it z sub alpha over 2. Specifically, because that's what it is, z sub alpha over 2. If we were to be super formal about this, this would represent the z value in the standard normal distribution with an area of alpha over 2 above it. Thankfully, though, we have easier means for finding this value than having to calculate this value of z every single time. And note, this specific textbook calls this value of z a critical value. So I will be referring to this as a critical value, the whole thing, by the way, not just the subscript, from here on out. Let's get a little deeper into that, into those critical values. There is now a new table that you will be using called a t-table. Looks like this. It'll be in your formula packet. In this t-table, there's something called a t-distribution. You don't know what that is yet. You don't have to worry about that yet. But at the bottom of this t-table, you're going to find something very interesting, the variable z. It turns out that the entire bottom row of this table are the critical values represented in our confidence intervals. So I'm going to show you how to do this in a second, but what's going to happen is you're going to be presented with a confidence interval, and when you go to calculate this, you're going to bring some information with you. You're going to go to the bottom row of the t-table, and you're going to locate the number that you need to plug into the formula. Okay, so let's take some time right now and focus on this critical value. We'll get back to the confidence intervals in a second, but we need to develop the skill and the understanding of how to use the table, similar to how I helped you understand how to use the z-table. Okay, so let's start out with something very important here. In every confidence interval problem that you do, there is going to be something called a confidence level associated with that interval. The confidence level is what it sounds like. It's your amount of confidence you have in your interval. So just remember that we are using a sample proportion to estimate a population proportion. There's no way, given the error involved in this, with only a small part of the sample, that we're going to be 100% confident in the results. Therefore, this confidence level right here is going to give us the exact confidence that we have in our results, specifically in our confidence interval. So really, the big question here is, how does knowing the confidence level have anything to do with the critical value? Well, it would be very useful for us to know the value of alpha. Why? If we knew the value of alpha, then we could plug it into that little subscript right there. We could divide it by 2, and that would tell us the upper tail area of this value of z. Now again, we're not going to do the calculation. What's really neat about this is that if we go to the t-table, which we already said has all the critical values at the bottom, if you go to the top of the table, what it shows is all of the upper tail areas. So if we know what the upper tail area is, we can find it, take that column, whatever it is. So let's say it was, I don't know, 0.15 or something like this. We could go all the way to the bottom and find the appropriate z for that upper tail area. That's what, for now, we'll be using the t-table for. So again, we would really like to find alpha, and it turns out that the confidence level is going to get us there. The answer for how that's going to happen falls within this part of the declaration for our confidence interval for a population proportion. You're going to see something called 1 minus alpha. Okay. This entire portion of the statement actually refers to our confidence level. So what it's saying is, whatever value you get for 1 minus alpha, you're going to multiply by 100 to get the percentage or our confidence level. So just as an example, so let's just say that our confidence level is 90%. Okay, so if we were to work backwards and drop the percent and divide by 100, so work backwards to the decimal equivalent of 90%, what are we going to get? We're going to get 0.90. That is the decimal equivalent. So just to be clear, so if this portion right here was 0.90, I would multiply that by 100, get 90, and then tack on the percent to get a 90% confidence interval. So this portion here, 0.90, is going to be equivalent to 1 minus alpha. What this does is this creates a direct relationship between the confidence level, which is here, the decimal equivalent of it, to be specific, and the value of alpha in basically a mini algebra problem. So what could we do? We could add alpha this way and get alpha plus 0.90 is equal to 1. And then that means we could subtract 0.90, and we're going to get alpha equals 0.10. So believe it or not, we can find alpha whenever we know what the confidence level is. Now, you could do this math every time, but the reality is there's a quicker way. Why? You're going to notice that our two values of our confidence level decimal equivalent and our alpha always are going to have a sum of 1, which means if you have one of those, you just have to subtract from 1 to get the other. Okay, so let's use that and the table in order to find the appropriate value. So let's say, again, we know that our confidence level or let's say our confidence level is 90%. So we know that the decimal equivalent is 0.90. So in order to find alpha, all we have to do is subtract that from 1 and get 0.10. So what do? We go to our z sub alpha formula, z sub alpha over 2. We plug in our 0.10 into the formula, and we get 0.05 when we do the little math. In order to find the value, the critical value z sub 0.05, we go into the t-table. We find 0.05, we go all the way to the bottom of this row, and we locate 1.645. So The value that we're looking for our critical value is 1.645, which will go here. Oops. Will go here in the formula for margin of error, which tacks on to our confidence interval. Before we move on to a full example of a confidence interval, there is one set of important requirements that must be mentioned when it comes to utilizing this formula. This formula will not be accurate for this confidence interval unless these requirements are met. Okay, here are the requirements as shown. So the first major requirement for this confidence interval is you must have a simple random sample taken from your population. That is very sensible. We want to make sure any bias is taken out of this. The second requirement is a one or the other situation, and I'll explain. So our first requirement here is for specifically very large populations. Whereas our second requirement is for small populations. I'll explain. So the first one should be familiar to you. It looks a lot like the normality requirement for sampling distributions of a sample proportion. It's almost identical, except with the fact that the P, the population proportion P that was in the formula here and here, is replaced by P hat. Well, that is not any different from our actual formula that was our P's were replaced for P hats. Because of the fact there is no P, it's unknown, we're trying to estimate it. So all we're doing is replacing P hat and P with that formula. If we want a normal distribution for our confidence interval, which is what we're looking for, then in large populations, we just have to make sure this requirement is met. Okay, we're not as lucky in small populations to use the first requirement here. Instead, it actually doesn't work well and create normality. So instead, what we have to do is we have to use this one. This is basically saying that little n is less than or equal to 5% of big N. So what does that mean? That means that our sample size must be less than or equal to 5% of our population size. We don't want our sample to be a huge part of our population. We want it to be small enough that it's legitimate for running the study. And if it is true, then we conclude normality. Okay, so you now have the components in order to do a full confidence interval problem. So let's go ahead and do so. It says in a random sample of 250 employed people, 61 said that they bring work home with them at least occasionally. Compute a 90% confidence interval for the true proportion of employed people that bring work home. Okay, so we're clearly here dealing with proportions. As a matter of fact, we can immediately see that we're dealing with a sample that yielded 61 out of 250 that bring work home with them. This value, if you calculate it, will get you 0.244 as your sample proportion. We also know that our sample size right here is 250. The problem is clearly asking for the confidence interval for the true proportion. So when I say true proportion, that means that I'm looking for P, our population proportion. Therefore, this is the exact requirements for using our 1 minus alpha 100% confidence interval for a population proportion. So that's what we need to do. So yes, we have the formula for that, but before we even get started, we want to hit those requirements, right? So our two requirements were that we had a simple random sample. You can see right here that we do. And depending on whether we have a large population or a small one, we use either this guy here or this guy here. Well, if we're talking about employees, that is an incredibly large population that we're dealing with. So as is the case with most examples from our class, we're going to have to verify that this is going to be greater than or equal to 10. So we could do that right now by just simply doing 250 times 0.24 times 1 minus 0.24, which is going to give us 46.1, which is indeed greater than or equal to 10, which means the requirements for this confidence interval are met, and we are confident in using that formula. Okay, so let's bring that formula back. So the formula for this confidence interval for a population proportion is going to be p hat plus or minus z alpha over 2 times the square root of p hat 1 minus p hat over n. So as was stated before, we are always given n and p hat, which you can clearly see are right here, right? So this ends up being a very simple computation once you have that, and once you know what your z alpha over 2 is. Now, I purposely, just so that I'm going to have plenty of examples later, but I purposely used the same one that we used before. We already know what our z alpha over 2 is for a 90% confidence, and that's 1.645. We'll get to more examples, like I said, later that will have different z alpha over 2s, but I'd like to just move through this to make sure you have one super straightforward example to go to understand. So let's say we start plugging in numbers here. So 0.244 is our sample proportion. We know that our z alpha over 2 is 1.645. And we also know that we, once again, throw in our sample proportion over here and divide by 250, which is our n. My suggestion to students is to always find the margin of error. So this is E, the margin of error. So do that calculation first. Absolutely do not do this together. That is not how you calculate a confidence interval. You always have to do the margin of error first and then add and subtract it from 0.244. So do this calculation. If you do so, you're going to get 0.0045. So basically, our margin of error is about 4.5% for this problem. So what do? Well, I'm going to do this in the way I'd like you to do it, and that's using interval notation. So the first thing we're going to do is we're going to do 0.244 minus 0.045, which is going to constitute the lower end of things right here. And then we're going to constitute the higher end of things, and we're going to do plus, after a comma here, 0.045. We then put this together with a little bit of mathematical computation and get 0.199 and 0.289 as our two values for the ends of our confidence interval. So to be clear, we do not know what the true proportion of employed people that bring work home is. We used 0.244, our sample proportion, as a point estimate or a guess, basically, on what that will be. But we now have a better understanding of what P could be. It could fall anywhere in this span of numbers, our confidence interval. Along with every single confidence interval that you compute, you will also be asked to interpret. So let's interpret the interval. Okay, this is a set form sentence that you will replace words in that you have to memorize, basically, and will be graded that you know it on your exam. So let me write it out first, and then I'll explain. We are 90% confident that the true proportion of employed people that bring work home is between 0.199 and 0.289. So basically, what are the areas that you would change when you go to a different problem? So if it's a different confidence, you change that. The context obviously is going to change. So this is employed people that bring work home, but it could be anything. And of course, you're going to change these two numbers based on your span. But this is the interpreted statement that you always will need to accompany your computed confidence interval if it's requested, obviously. So if I don't say to interpret, then you don't have to actually include it. But if I say compute and interpret, this is what you must write after your interval. All right, let's do one more example, and then we'll leave the rest for part 2 of the video. It says a poll was taken of 1,010 randomly selected U.S. employees. The employees sample were asked whether they play hooky at least once a year. It turns out that 202 responded yes to indeed calling in sick just to rest, even though they are perfectly healthy. Letter A, it says determine a 95% interval for the proportion of all U.S. employees that play hooky at least once a year. So once you see that this is a proportion confidence interval that's being requested, then ideally you want to get in the mindset that you're going to be looking for three things. You're going to be looking for the sample size n, you're going to be looking for the sample proportion p hat, and you're going to be looking for the confidence level. The confidence level sticks out right away at 95%, but in terms of our other information, we have 1010 as our sample size, clearly right here. But they don't give us p hat explicitly. They give us the value of x for x over n, which is 202. We can easily compute that sample proportion by just taking 202 and dividing by that same sample size and getting 0.2. Okay, we might want to just check out the requirements here to make sure this proportion interval is even valid. We have a simple random sample. I did add this, by the way, just now. Just because it wasn't there, it should be there. It is a random sample, but SRS, if it wasn't, then we'd be skeptical about whether the interval would work or not. So we're going to make it randomly sampled. But our second requirement is either one of those two normality steps. If you recall, they were right here. Right here. So if it's a large population versus a small population, so we're actually dealing with all U.S. employees. So that is an incredibly large population, which means we don't have to worry about the right part. So we just have to be able to do this np hat. np hat 1 minus p hat. That is going to give us 1010 times 0.2 times 1 minus 0.2. This will give us 161.6, which clearly is greater than or equal to 10. So normality is good. So right now, we're going forward assuming that this proportion interval is valid. Okay, so here's our proportion interval formula that you would get from your formula sheet. Just remember that n and p hat make up the majority of the formula, so most of it is just plugging in numbers, but we need to be able to find this critical value right here, and the only way to do that is to determine alpha. So remember that alpha is always going to be equal to 1 minus the decimal equivalent of our confidence level, so 0.95. That is going to give us 0.05. But we don't want alpha. We want alpha over 2, which is going to be 0.05 over 2, which is 0.025. So basically, this right here is going to be z sub 0.025. Okay, so the rest is basically just filling in formula pieces. We have our p hat 0.2. We have our z sub 0.025. So just remember, you go to the t table for these guys. So let me just get rid of this old stuff, right? So we always go to the upper tail area, which is 0.025. That's going to be right here. So then we go down this middle column here, and so we get 1.960 as the value we need for our critical value. We then multiply by 0.2 times 1 minus 0.2 over our 1010. Okay, as I mentioned in the previous problem, always good immediately to find the margin of error here. It saves mistakes. Students often do this a little bit wonky with the PEMDAS. So just find this margin of error right away. Remember, this is the entire right side of the interval after the plus or minus. Also, don't be surprised on homework or an exam if you're asked straight out for the margin of error, and that's it. So make sure you understand that this right portion is that, and that's what they'd be looking for. So once you have this, then all you have to do is your interval. So you're going to have 0.2 minus 0.025 on the left side of the interval, the low end, and 0.2 plus 0.025 on the right end. If you do the computations for this, you're going to get between 0.175 and 0.225. Okay, let's also talk about the interpretation, which I wrote out here to save time. We would say we are 95% confident that the true proportion of U.S. employees that play hooky is between 0.175 and 0.225. Again, the problem asks you to interpret. This is what you would write. I again highlighted the portions of this little form sentence that you would replace for every individual problem. Okay, just one more critical thinking question here. It says a local company claims that 15% of their employees play hooky at least once a year. Is that company consistent with the rest of the country? Okay, so what we've basically done is we've come up with this interval here, in order to judge what the true proportion for the rest of the country would be in terms of a proportion who play hooky. So we've basically what we ended up with is we're between about 17.5 and 22.5%. So let's say a local company claims that 15% of their employees play hooky once a year. Well, if you look at that 15% here, it doesn't fall in the interval. We're basically, by making this interval, we're saying we believe the true proportion is in here somewhere. And that 15% is not. So we would say, no, we don't believe it is, because the P equals 0.15 that they claim play hooky does not fall in our confidence interval.